Okay, welcome back to another one of these kind of grade 5 to grade 9 full explanations of different topics. And today we're going to do circle theorems, which are pretty much the bane of some people's existence. But with this, it's all practice, because these are all the circle theorems you can be asked to know, or you're expected to know. And again, they're very hard to remember. So I personally never kind of sat down and memorized these. I just kept using them over and over again. And eventually they just started popping into my head when I saw certain questions on circles. So I've put this on the front page of the question, so remember in the description you can download the PDF of all the questions we're going to do and either do them first and use this as a mark scheme, or you can do this kind of like a few days after this video, after you've watched this video, and then you can kind of retry them. But this is going to be the front page of it, so you will have these to reference whenever you need to. Now, here are the questions we're going to do. So this first one, it says B is a point on the circumference, AB is a tangent, and BOA is 72 degrees. Work out the size of BAO, which is BAO is going to be this angle right over here. Okay, so we'll call that X maybe. Now, which circle theorem are we going to use? Well, if we look at the circle theorems here, we have a tangent and a radius, which if you look here, tangents meet radii at 90 degrees. So in other words, this is a big right-angled triangle. Okay, which means X is just going to be 90 plus 72 and then subtract it from 180, because remember, angles in a triangle add up to 180 degrees. So X is just going to equal to 180, and then you're just going to minus 72 plus 90. So 72 and another 90, which will give you an answer of 18 degrees. Because 72 plus 90 is 162, 180 minus 162 is 18 degrees. And again, for your reason, you would just say that tangents meet radii at 90 degrees. Cool. With the next one, so we're going to be starting off with the easiest possible questions, the simplest ones, and we're going to move on to the harder ones as we go forward. So you can skip ahead if you'd like to go on to the higher grades. ABC are points on a circumference, and find the size of angle BAC and then give a reason. So this kind of circle theorem here is one that's very important. So its angles at the center are twice that of the circumference. So here it's going to be half the angle that it is here. So in other words, it's going to be 66 divided by 2, which is 33 degrees. And that is because angles subtended, so they use the word subtended, so essentially formed, angles subtended at the circumference are half the angles subtended at the center. So that might not make full sense right now, so let me explain it. Essentially, the word subtended means formed, okay? So the angle that's formed at the circumference is half the angle formed at the center. Now, what do they mean by this? Well, if you have a look, both of these angles, 66 and 33, are made up from the same 2 points, right? B and C, which is why we can say they're half of one another, okay? If, for example, instead of having that, we had an angle that started off here and was these 2 points, like this angle here would not be 33 because it's not subtended from the same 2 points, okay? So the key part here, and you'll notice this in a few circle theorems, the two kind of angles have to be made up from the same 2 points on the circumference, okay? So if you look here, we draw lines from B and C to get this angle. We draw lines from B and C to get this further back angle, and they're going to be half of one another. Okay, now, here's where things get a bit more spicy, 3 marks. So B and C are points on a circle, and AB and AC are tangents to the circle. Angle BAC, so this angle here, is equal to 40 degrees. So again, you need to be able to label up diagrams yourself sometimes. And we need to work out the size of the angle BOC. So I need to actually draw this angle on. So BOC would be a line going from here to here, here to here, this angle here, okay? And we need to work that out. So how can we do that? Well, there's a few things that we can remember. Is first of all, radii meet tangents at 90 degrees. And as you can see, because it's going from the center of the circle to the circumference, it's always the radius, okay? Now, the other thing that's quite interesting is that tangents from the same point are always the same length. So both of these things are the same length. And obviously these two things are also the same length. So this is actually a kite, believe it or not. So that's not too. There are a couple ways to do this now, because since these are all kind of symmetrical with each other, you can cut this shape in half, find out what it is and double it. But the easiest way is, think about it, right? This is a four-sided shape. What do the angles in a four-sided shape add up to? They should add up to 360 degrees. Now, how much have we got so far? We've got 90 plus 90 plus 40. So 90 plus 90 plus 40. 90 plus 90 is 180, plus 40 is 220 degrees. So the leftover angle, BOC, is just going to be equal to 360 minus 220, which is 140 degrees. And you should find that you get that no matter which way you do it. Perfection. Now, we have this shape. So this is where things can get a bit kind of spicy when it comes to having circle theorems. A, B, C, and D are points on the circumference of a circle. CAD is equal to 62 degrees, and BDA, or ADB, whichever way around you want to do it, is 51 degrees. So, we need to find the size of the angle ACB. So we're looking for this angle here. Remember, when you're looking for the angles, the kind of ACB thing, it's always just the one that's in the middle, so the letter in the middle. So we know we're looking at an angle at C, and then we look at A and B, so those are the lines that make up the angle, so we know it's here, okay? And we need to give a reason. So, here's what we're going to do, and I'm going to hopefully try and do this in an easy, like a very obvious way, okay? I'm going to say that this is 51 degrees. Now I'm going to do the explanation afterwards, which might seem a bit weird to you. And the reason is angles in the same segment are equal. Okay? Now if you remember what a segment is, right? All it is kind of a curve. So if I draw like another circle out, right? A segment is essentially this pizza slice is a sector, but if you were to draw it here, the segments are this shape here, okay? So essentially if two angles share the same curved part, they're equal. So now I'm going to show you that this angle here and this angle here share the same sector, right? If I look, both of them are formed from the points A and B, right? Which means they both share this shape, this curve here. Can you see that? So if I were to kind of draw it out, let's use a green highlighter for this one. That's the two sides for angle D, and let's say orange for C. And that's the two for this. So can you see that both of those angles share this same curved shape, right? Because they're both formed from the same points on the circumference, which means they must be equal, okay? So hopefully that makes a bit of sense. Again, all you need to do is look at what points the angles are formed from. Angle D is made up from a line from A and a line from B. Likewise, angle C is made up from a point on A and B, which means they share the same curved part, which means they share the same segment, okay? Perfect. Let's keep going. This next one, it says A, B, C, and D are points on the circumference of a circle. And it tells me that this angle and this angle, find the size of angle A, B, C. Now, if you notice, all four corners, all four vertices, are on the circumference of a circle. All four of them have to be this, which means it is a cyclic quadrilateral. Okay? So, that is a really important thing, because if you look back at your circle theorems at the front, when it comes to cyclic quadrilaterals down here, opposite angles add up to 180 degrees. So, I'm looking for the angle ABC, which is this angle up here, and that is opposite to this angle, 83. Both of those should add up to 180. So in other words, the angle ABC is 180 minus 83, which is 97 degrees. And now we have to give a reason. And again, what you'll find in circle theorem questions, it's a really important exam technique, is it doesn't matter if your working out's perfect, doesn't matter if you get the right answer, you'll get 0 marks if you don't give a reason when they ask you for a reason. In most of the later papers, they always ask for a reason 100% of the time, okay? So you need to actually know the wording of the circle theorems, otherwise you will get 0 marks in total, even if it's a 4 or 5 mark question. So the reason for this is that opposite angles in a cyclic quadrilateral, and again it's cyclic because all 4 corners are on the circumference. Okay, and that's a really important thing. If this one wasn't on the corner, it was over here somewhere, that's not cyclic. Not 3, not 2, not 1. All 4 have to be on the edge of the circle, okay? Okay. Now for this one, we have A and B are points on the circumference with the center of O of a circle. ABO is 48. Find the size of angle AOB. So we're looking for this one, and we need to give a reason for our answer. Okay, so it doesn't look like they've given us much, but they've actually given us everything we could possibly want. Okay, and here's what you need to do. The first thing I do in any circle theorem question is I label up stuff that I can kind of infer, right? Now O to A and O to B are both the radius, right? Which means they're both the same length. Now I'm willing to bet you've now worked out what the answer is. This is an isosceles triangle, which means both of these angles are 48 degrees. The angles in a triangle add up to 180. So we do 48 plus 48, which is 96 degrees. And then we're just doing 180 minus 96 degrees. And that will give us our answer. Okay, so just labeling stuff up can, generally speaking, get you towards the answer, especially with some of the harder grade 9 circle theorem questions, okay? And that is 84 degrees. And what is the reason for this? Well, this is kind of an interesting one. There are 2 reasons you could give. First of all, you could say base angles of an isosceles triangle. So base angles of isosceles triangle are equal. And the kind of next reason, and you can write both if you want to be kind of super secure, is that angles in a triangle add to 180. So I understand that writing out reasons for every single question is quite tedious, but keep in mind there's generally speaking only one circle theorem question that comes up each year. So when you're revising, you could even work that in, maybe do 2 or 3 questions a day instead of trying to do 10 at once, right? So even in the paper that I'm leaving in the description, I think there's 20 questions or 18 questions, something like that. You can do a couple of them a day instead of doing all of them at once, which will kind of help you not get fatigued, so to speak. Okay, here's where things are getting slightly more tricky, okay? We're probably looking at around grade 7. So A and C are points on the circumference of a circle centre O. A, B and BC are the tangents. Find the size of the angle OAC. So again, label up what we know. Those are both equal in length because they're both tangents from the same point. They're both from B. These angles here are 90 overall. So I'm not looking at OAC. I'm looking at OAB, right? The whole angle, not the small one. And what am I trying to work out? OAC. Okay, cool. So I'm trying to work out this tiny piece of this one here. So let me think about what I want to do. Well, here's what I think. If I were to remove this line here, right? Imagine it didn't exist. That looks exactly like a question we did before, right? It looks exactly like this question, right? If I add the line here, then we suddenly have the same question. So if I imagine this line isn't here and I look at the whole shape, I can work out the angle at O because I know that the line OA to OC are both radii, right? Which means they're both equal. So if I know the angle at O, 180 minus that would give me these 2 angles added together, divide by 2 and we're done. So to work out the angle at O, all I'm going to do, so if I call it AOC for example, I'm going to add up 90, 90 and 46. So 90 plus 90 plus 46. 90 plus 90 is 180 plus 46 would be 226. It's going to equal 360 because again it's a quadrilateral minus 226. Okay, which is equal to not 67. It's going to be 100. It'll be 100 and then 114. Not 14. 24. No, what am I talking about? 134. Jesus Christ. 134 degrees. Not sure why that was so difficult for me. Anyways, 134 degrees. Okay? Cool. So, if we... Actually, no. Yeah. If we look at this now, we have this angle at the centre over here. All we need to do is subtract it from 180, divide by 2. So we're going to do 180 minus 134, which is 46 degrees, right? And then angle OAC is just going to equal half that, 46 over 2. And again, this is one of those questions, if you look at the last line here, it says give reasons for each stage of your working out. So for this one, you'd say, angles in a quadrilateral add up to 360, right? Angles in a triangle add up to 180. Base angles of an isosceles triangle are equal. And that's 4 marks, so you do get marks for the reasons, essentially. So keep that in mind. That's a very tricky question, or at least it's getting into the kind of grade 7 territory. Again, you need to give reasons. So here, angles in a quadrilateral add up to 360, angles in a triangle add up to 180, base angles of an isosceles triangle are equal to each other. Okay, so again, we're continuing with the kind of grade 7 kind of questions. So, what do we have here? A and B are points on the circumference of a circle centre O. DCE, so this straight line here is a tangent. ACD is this, cool. Find the angle of ACO. So ACO is this tiny little sliver over here. So, and it does say give reasons for each stage of your working out. So, OC is the radius, this is the tangent. So these should add up to 90 degrees, a right angle. So in other words, ACO was it? Yeah, ACO is just going to equal 90 degrees minus 76, which is 14 degrees. And the reason would be tangents meet radius, technically B meets radii at 90 degrees. Done. Then find the size of the angle ABC. So ABC is this angle over here. So again, we can kind of think about how this is going to look. Now, the equation, this is the one that I'm going to use, is a fairly tricky one to kind of describe, okay? Now, I'm just going to write the answer for now. I'm going to say it's 76 degrees. And the reason is the hardest one you'll ever do. This is the hardest circle theorem in my opinion because it's very difficult to spot. It's the alternate segment theorem. Okay? Again, it's incredibly difficult to spot. So let's go up to see what the alternate segment theorem is. It is over here. Okay? So if you look, if the angles are kind of on the opposite side to each other, right? One's inside the triangle, one's outside the triangle, they're going to be equal. To read the full description, the angle that lies between a tangent and a chord, so can you see that AC is a chord in this sense, is equal to the angle subtended by the same chord in the alternate segment. Okay? So if you look, BC is a chord, AB is a chord, AC is a chord, so we have chords everywhere. So if I scroll down to the question we are doing here, we have a chord AC, right? Now, and we have a chord BC here. So we have these two chords that meet up with each other, okay? Which means that the two angles here are equal to each other. Now that might sound very difficult to kind of process, but here's a little bit of a hint. They will always give you a triangular shape when it comes to the alternate segment theorem, because that's the kind of most common example of it, okay? So all you need to know is that whenever you have a triangle, if you have these two chords touching each other, then the angles opposite are always going to be equal. Now this does actually mean that this angle here is also equal to this angle here, because again, there's two chords touching each other and they're opposite to each other. So whenever you have a triangle, okay, just think about the kind of alternate segment theorem, because you have two chords touching, you have the opposite angles equaling each other. I hope that makes some vague amount of sense. And as we kind of move swiftly on to the next style of question. So we have all these points on the tangent, cool. ODC is 26, cool. Find the size of angle BAC. So, BAC, let's look where that is first. BAC is this angle here. And so what I'm thinking, right, is I'm thinking of using that angles subtended at the circumference are half that at the centre. So if I can work out what this angle is, that would be really useful. Now, I've had a bit of a brainwave, okay? If I have a look at OBD, the shape, the triangle, and ODC, they are actually congruent. They are identical. Why? Because of ASA. So tangents meet from the same point are the same length, okay? They also share this length here between each other. So both of these triangles are actually congruent to each other because of ASA, right? Technically, you can also use SAS, right? In fact, this is SAS, not ASA. The reason why I was saying ASA is also because these meet at 90 degrees, which means you can also use RHS. So don't forget, when you use congruency, all of the congruency criteria are true at the same time because they are the same, right? So we have SAS because we have two sides and the angle between them. We have ASA because of the two angles and the side between them. And also here we have angle, side, angle is going to be the same. And lastly, we have RHS, so a right angle triangle, hypotenuse being shared and one side being the same. So in other words, if I work out what this bottom angle is here, I can double it and then half it again, funnily enough, to get that angle there. So let's go. So if we call it angle COD, that's equal to, well, it's 90 plus 26, which is 116. So we're doing 180 minus 116, and the reason for that is angles on a triangle, angles, triangle, add. So yeah, I'm writing a bit like a caveman because I'm getting a bit lazy. But anyways, that would give me 64 degrees. Okay? Now, because the two triangles are the same, then angle BOC is equal to 2 times 64, which is 128 degrees. And again, that's because OBD and ODC or OCD congruent due to, let's just call it SAS, right? Now, BAC is just going to equal half of that, right? Because angles subtended at the centre are twice that at the circumference. Which is back to 64 degrees again. And again, angles subtended at circumference are half that at the centre. Okay, so angles subtended at the circumference are half that at the centre. Whew. So again, these questions, if you notice, it's 4 marks, right? So these are grade 7 questions, 4 marks. They're quite short in terms of the amount you have to do. And in terms of the maths, I'm just adding numbers, subtracting and timesing, dividing by 2. So it's not too bad. But obviously the difficulty is knowing the circle theorems. There's quite a few that can be used. So I'd recommend just practicing as much as humanly possible, which again might be a bit of a shocker, right? This style of question, okay. Again, just like with vectors, right, they're very tricky topics, but there's a limited number of kind of situations they can put you in. This is a very common situation, and I've actually been emailed about questions that are the same as this, except different numbers here or here. That's literally all the difference is, right? And it's always the same, okay? So you're always going to do the exact same things, which might seem like a bit of a cheat, and it is, but you can always use these techniques I'm showing you, okay? They'll only give you a certain number of different situations. Here's what you do. You draw a line from O to C, or whatever the bottom one is, because that makes it 90 degrees. And it also means that this is an isosceles triangle, which makes that 29 degrees. Now I can work out any other angle I want. So I don't even know what they're asking me yet. I don't need to know. Find the size of angle ABC, so in other words, they want me to work out this angle. That's child's play now. All I've done is drawn a line. So, key point here is the second they give you a kind of situation like this, just before even reading the question, just draw a line straight down from the centre to whatever the other point is on the circumference. Technically, they could, if they wanted to, they could flip this upside down so the triangle's going up. It won't make a difference, just draw one straight going straight up. Anyways, ABC. Let's work it out. You must show all your working. 4 marks. Again, you're going to find this is really, really easy. We can't work out this angle just yet because we only have one angle here. But we can work out this angle here because this angle we can work out. And then we're going to do 180 minus it and then do 180 minus it again. Right? So, angle AOC is equal to, well, keep in mind, base angles are the same. So we have 29 plus 29, which is 58. So that angle there is 180 minus 58, which is 122 degrees. Cool? Which means angle COB is equal to 180 minus 122, because again, angles on a straight line add up to 180, and that would be the reasoning. In this case, they haven't actually said to show your kind of reasons for your working out, so I don't have to, but I'm going to say them instead. So the first one, base angles in an isosceles triangle are the same. Second line, angles on a straight line add up to 180, right? Because that would be a whole straight line. Lastly, angle BOC. Well, the first thing we need to do before anything is we need to add the 58 degrees from up here, right, to 90, which is 148. And we're going to do 180 minus 148. And the reason for that is that angles in a triangle add up to 180. So 3 lines of working out, 3 reasons, 4 marks in total. It's actually relatively generous, okay? Again, if you're saying, how will I know to do that? Well, you wouldn't have, but now you do, right? If you ever get given a triangle where one point is outside of the circle, you know what you're going to do is draw a line from the center to the other point on the circumference, okay? So we have 2 points on the circumference, 1 outside the triangle. The method is always 100% the same. Draw a line from O to C, move on from there, okay? All you got to do. Okay. Voice is getting a bit tired now. Anyways, A, B, and C are points on the circumference. And, okay, before we even get started, I have a triangle, right? So what am I thinking? Alternate segment theorem. That should now be in the front of your head. Again, it doesn't mean you will use it, but I'm willing to bet my house that we will. But just put it in your head so you can spot it. DCE is a tangent, cool. Yeah, again, we have the same situation, right? Tangent and 2 chords. Angle BCE is X. Find the value of X. Well, here's what I know. And there's 2 ways to do this. Both of them are acceptable. Angle X is the same as angle X over here because of alternate segment theorem. How many marks is this? 3 marks? I'm going to do it in 2 lines of working out. That's all you have to do. So you can even write that angle BAC equals BCE. And if you notice, it's the same layout as we had before, except they flipped it round. But if you ever have a triangle where all the points are on the inside, right, they're all on the circumference, and a tangent, you're always going to be using alternate segment theorem, okay? Now the other way to do this, by the way, because I mentioned there was 2, is you can also say that this angle here is 61 degrees, and therefore x is just equal to 180 minus 61 minus 73, because angles on a straight line add up to 180. But if you notice, you're going to do the exact same working out, fundamentally, so it doesn't make a difference, okay? And all you do is write alternate segment theorem. I hope alternate segment theorem is getting a bit less scary, now that you can see that it's always the same kind of layout. It's just pattern recognition. And so x, so BAC, equals x, and it equals, well, first of all, let's do 73 plus 61. So 73 plus 61 is going to be 134. So it's 180 minus 134, which is 46. And that's because angles in a straight line, angles in a triangle add to 180. So once again, it's the exact same thing, right? As previously. Oh look, I have another triangle and I have a tangent. So I wonder what I'm going to think. I'm going to think alternate segment theorem. And literally, I'm not even kidding. Because I've done so many of these questions, I'm literally thinking that the second I see this. Like, if you show me a picture of this, even in a non-maths context, I'm just thinking alternate segment theorem straight away. Okay? And what does that mean in this case? Well, it means that this angle and this angle are the same. And it also means that this angle here is 65 degrees. And I think I've accidentally just solved the question. All right. Find the size of angle AOC. Okay, that's a little more tricky, thankfully, because otherwise I would have just accidentally solved the question. What we can do, and there's a few things we can do here. What's the quickest way? Well, it's a 4-mark question, so maybe there isn't like a necessarily quickest way. What we can do is... Okay, I think this would be the best. What we can do, he says for the 3rd time, is... Oh, yeah, well, there's loads of things. Okay. I'm going to try and work out the angle at B using the fact that it's the same as the angle at DCO. And then I also know that in total it's like 90 degrees, right? Which means I can work out the inside bit of this angle. Okay? So that's what I'm going to do. So, angle at B, well, this is also going to be 65 degrees. Right? Because it's an isosceles triangle. So let's remove some of the other stuff. So again, I'm ignoring the line from O to C for now. Okay? And what I'm going to do is I'm going to do that the angle at B, so ABC, is equal to 180 minus 65 plus 65, which is 130. Which is 50 degrees. Okay? Cool. Now I'm going to get rid of this for now. Now, ABC, and the reason, okay, I should probably write base angles in isosceles triangle, base angles, iso, same, right? We know that, it's fine. DCA, or ACD, however you want to put it, equals ABC, which equals 50 degrees, because of alternate segment theorem, again. Can you see how the shape looks the same every time? Like, it's just a triangle inside a circle. Yeah? So that means this angle here is 50. And what do we know about radii meeting tangents, yeah? 90 degrees. Because basically what I'm trying to work out, I've just realised I didn't even need to do that. We know that this angle here is 50 degrees. So this angle here is twice that, right? So what we can do, instead of doing all that, right? So we don't even need this last bit here, is, so I wanted to show you 2 different ways, but from there all you do is do the 90 degrees, find that angle, that's the same as this, 180 minus it, blah, 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 done. But the kind of elegant way of doing it is AOC is equal to 2 times 50, which is equal to 100 degrees, because angles subtended, right? Angles subtended at the circumference. In fact, I'll write it out. Subtended at the center 2 times circumference, right? And remember, you have to write it out fully, so don't follow my example here. Because again, they're actually made from the same segment, so it's 100 degrees. So we have 4 marks for doing 2 things, right? All I've done is done 180 minus these 2 things, and then I've said that it's twice that. That's it, 100 degrees. Which is really, really quick and easy, okay? 4 marks. And again, alternate segment theorem we could have used, right? We could have used it to work out this, which means we can work out that angle. 180 minus twice that angle would also give us 100 degrees. So there's 2 different ways of doing this question, which is nice. But in this case, I think that was probably the easiest way to do it. Yeah, not too shabby at all. Another 3 marker. Okay. So A, B, C, D are points on the circumference of a circle centre O. We need to work out the value of x. Okay. Now the mistake with this question is that people would say it's a cyclic quadrilateral, therefore 180 minus 118 gives me that answer. No. Cyclic quadrilateral means all 4 points are on the circumference. Okay? So, in other words, this is actually the opposite angle to 118. Now I can work out what that is. So ABC is equal to 180 minus 118. And again, the reason would be opposite angles in a cyclic quadrilateral add up to 180. And that would be 62 degrees. Now, x, right? So AOC, which equals x, is just 2 times that. Why, you may ask? Well, because angles at the center are twice that at the circumference. Because again, they're made up from the same 2 points on the circumference, right? They're both made up from A and C, which means x is just twice that angle. So hopefully you're spotting how kind of frequently we use the same techniques, right? Next one, 4-mark question this time. Okay, this looks a bit more interesting, but hang on a minute. I have a tangent and I have a triangle with all 3 points on the circumference, so I'm thinking alternate segment. Again, it's the hardest one in my opinion, but you can always spot when you need to use it. So we have these 2 bits. Okay, cool. Find the size of angle ACO. ACO is this piece over here. Okay, so they've made this slightly harder for us, and I do mean slightly. But as you can see from alternate segment theorem, this angle here should equal this angle over here, right? So let's do that. BAC equals 53 degrees, which is the same as, by the way, BCE. And again, that's alternate segment, right? Again. So I'm going to label that now, just so you guys can see exactly what we're doing. Now, again, what we're trying to work out this angle over here, right? So, again, there's a few things we can do, but I'm going to draw a line over here. Now, both of these are the same length. They're both the radius of the shape. Now, how can we work out what that angle is? Well, there's a few different ways we could do it, right? There's a few different ways. We could work out, for example, well, by the way, it's not just half of 53, right? That's one thing I need to get abundantly clear. It's not half of 53. It may look like it. It may end up being it, but we can't assume it. So I'm a bit stuck here. There's a few things we can do. This 53, right? This would be twice that, right? It would be twice that amount because angle subtended at the center, blah, blah, blah. So that's 106. Okay? So I'm going to say, we'll leave that as it is. All we need to do is write BOC angle subtended at the center are twice that at the circumference. And the reason why I'm doing this is because these 2 sides are also the same. OC is equal to OB, which means I can work out what this angle is, which means I know what the total angle is, which means I know what this angle is, which is I can do 90 minus it, okay? So this is getting a bit complicated now, but OBC is just going to equal 180 minus 106, and then we're going to divide it by 2 because it's an isosceles triangle. 180 minus 106 would be 74. Divided by 2 is 37 degrees. So that is 37 degrees, which means the total angle here is 27 plus 37, which is 64 degrees. Okay? Which means this angle is 64 degrees. Now I can just do 90 minus this angle would give me ACO. That's it. That's quite a lot. I'm hoping that makes a bit of sense. Hopefully. But let's get to it. So, DCA equals CBA, which is 37 plus 27, which is 64. Again, because of alternate segment theorem, but on the other side. And don't forget, tangents meet radius at 90 degrees. So, all we need to do is do that ACO 90 minus 64, which is 26 degrees, because radii or radius meets tangent 90 degrees. That's probably the trickiest one we've done so far. So again, we're getting into grade 8/9 territory. This is a cluster of working out, but hopefully you can see what I'm trying to do, right? So if we kind of get rid of some of the bits that I think up to here people are going to be fine with, 106, then this small angle here would be 37, because this is just an isosceles triangle. So the total angle here would be 64. I hope that makes a lick of sense. Okay. Find the length of... Okay, this is actually pretty damn interesting. A and B are points on the circumference. Cool. Tangent, wonderful. So that means it's a 90 degree. And we need to find the length of BC, which, if you notice, is not the full length. Okay? But this actually isn't too bad. It's 4 marks, by the way. It's pretty good. Why is it not that difficult? Well, let me show you. If we work out using Pythagoras from O to C, can you see all we need to do is do 5 squared plus 12 squared, right? Because our hypotenuse is C. So we're going to do 5 squared plus 12 squared and then square root it, which gives me 5 squared is 25, it's 144. So that's equal to the square root of 169, which I'm sure we all know is 13 centimeters. Right? Now, this length and this length are equal. So O to B is 5 centimeters, which means B to C is just equal to O to C minus O to B, which is equal to 13 minus 5, which is 8 centimeters. Right? Because again, this first part here is 5. The total thing is 13, so I'll add that to the diagram just to make it make a bit more sense. So the leftover bit, BC, is just going to be 13 minus 5, right? Nice and, well, I'm not going to say easy, but acceptable, I think. Okay. So this is where things get a bit more interesting. This is one of the circle theorems we haven't used yet. Now, funnily enough, someone guessed this right, and because it didn't say give a reason for your answer, they got the marks by guessing. And what I mean by guessing is that they guessed that this is 90 degrees, and it is. So if this question were to come in the 2023 paper, bear in mind you need to give a reason. Now the reason, if we go all the way back to our beginning value, where is it? Angles in a semicircle. Basically, if you have one of your sides as the diameter, it is always a right angled triangle. So let's go all the way down, 14, 15, 16. AB is the diameter. Why? Because it's a chord that goes through the center of the circle. So that's the key part here. ACB, and I know it's not asking you to show this in the question, but it's 90 degrees, and the reason for that is angles in a semicircle. So just as a kind of recap of exactly what the hell I'm talking about, right? AOB is the diameter. So basically it cuts the circle in half, so it's a semicircle. If you then have the last point on the circumference, it's always, 1000% of the time, a right angle. So if one of your sides is that diameter and one of the points is on the circumference, right, the other point's on the circumference, it's always 90 degrees. So even if I drew like one over here and I drew a line here, it's 90 degrees. It doesn't matter. So again, one side's the diameter and the other point is on the circumference, always 90 degrees, always right angle. And therefore, this becomes a lot easier now. We know that the angles in a triangle add up to 180. Good lord, almost. So then we have 5x plus 90 equals 180. So 5x equals 90. So again, all I'm doing here is minusing 90 from both sides. Divide by 5 both sides. The way I divide by 5 in my head is I divide by 10, so 9, then double it. So x is equal to 18 degrees. 3 marks. Again, some of these aren't really like too bad, but you know, in an exam it can be kind of overwhelming. Oh look, all 4 points on the circumference, which means ABCD is a cyclic quadrilateral. Find the size of angle BCD in terms of x. Okay, BCD, this angle over here. Okay, in terms of x, that's completely fine. Well, I know that this, which is angle BAD, is half of x, right? Because remember, if we had like a number here, like 100 degrees, you would say angle A is 50 degrees because you half it, right? So again, with algebra, it's the same thing. You're just dividing it by 2. And the reason is angles at center, or angles at circumference, are half that at the center. So we're just halving it. And now, opposite angles in a cyclic quadrilateral add to 180. So what we know for angle BCD, so this angle over here, is that BCD, and again, imagine if we actually had a number, let's say 50 degrees. What would you say? You'd say 180 minus 50, right? Well, instead of 50, we have x over 2. So it's 180 minus x over 2, and you're done. And again, op angles in a cyclic, blah, 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 add up to 180. Cool. Oh, look, we have a triangle where it has, good lord, triangle with all 3 points on the same thing, so blah, 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 alternate segment. In fact, this looks exactly the same as one of the other questions we did. These are exam questions, right? Which means they have reused the same shapes, and the method is the same. So instead, they're telling me that angle AEC is this part here, is equal to x, and we need to work out the size of angle OED. So OED is this one over here. Okay. Work out, find the size of angle OED in terms of x. So again, okay, doing the same thing, but instead of numbers, we're using x, but that shouldn't make a difference, right? Remember, letters are just numbers we don't know, okay? So, here's what we'll do. This angle here is equal to x. Alternate segment theorem, right? Hopefully you're getting good at spotting that now. And hopefully you see that from watching these videos, right, that by the end of it, you're like, actually, this is kind of easy. Because it's all just practice. All you need is someone to show you how to do it, and then you're completely fine. But I would recommend actually doing some practice yourself, okay? Watching is a very passive experience, so try these questions a couple days after you watch this video, or even before you watch this video if you want. And then if you make a mistake, then you know how to correct it, and that's a better way of doing things. Okay, so OED, so what we can do here is, well, there's a few things. We know that both of these angles here are equal to each other. So in other words, we have DCE equals, what should we call the other one? DEC? Are equal, and they equal to 180 minus x, and then we're halving it. Do you remember? Because it's isosceles triangle. Base angles of isosceles triangles are the same. So we 180 minus x, so it gives me 180 minus x, then we're halving it. So if we actually want to do this halving, we have 90 minus x over 2. Again, we're doing the same steps that I did in the previous question, except instead of having actual numbers, we have x, which is fine. So this total angle here is 90 minus x over 2, which means COE, this is quite an important thing. So the way we're going to work this out is if this total angle here is 90 minus x over 2, if I work out what the angle C kind of OE is, or even like CEO, I should probably say, CEO, right? If I work that out, I can just do 90 minus x over 2 minus whatever this is. So CEO is just equal to, remember, these add up to 90 degrees, right? So we have 90 minus x, yeah? And the reason for that is tangents, radius, 90 degrees. So, all we need to do now is do for angle O, what do they call it? OED, right? OED is just equal to angle, what angle should we call that? CEO, that's what I called it. Not CEO, we're going to do 90 minus x over 2, which was DCE. Yep, DC minus CEO. Right, so the total angle here is 90 minus x over 2. This tiny angle here is equal to 90 minus x. So we're going to do that now. We've got 90 minus x over 2 minus, and I want to put this in brackets because a lot of the mistakes that people make is when they minus a value, when it has two parts to it, they don't put both parts. So don't forget, we're minusing 90 and we're minusing x. So now if we expand the brackets, we have 90 minus x over 2 minus 90, but then the minus and the minus here becomes plus x. So the 90 and the 90 cancel out. And what is x minus x over 2? That's 1 minus a half, which is just x over 2. 5-mark question. Done. Deasy. Okay? So just be extra kind of careful about that, okay? The minuses will cancel out with each other. Which makes sense, right? We shouldn't get a negative number.